So now let's look at an example of a unit conversion. And if you recall from the first part of this section, I said that what we need is an equivalent statement. Well, here we have a degree of an equivalent statement. We now know that 1 kilogram can be considered to be equivalent to 2.2 pounds. Now, the reason that I wrote it like this as a fraction is if these things are equivalent, then effectively I'm multiplying by 1. So I'm going to take 187 pounds and I'm going to multiply that by 2.2 pounds, and I'm switching from an abbreviation to the word just for 1 kilogram. Now the reason that you want to make sure that in this case we could also have said 2.2 pounds is equivalent to 1 kilogram. That's perfectly fine, but from a mathematical perspective, we want the pounds units in the denominator so that we effectively cancel these out. And so we're left with 187 divided by 2.2 kilograms, or 85 kilograms. Now let's look for a moment at significant figures. This has 3 significant figures because all non-zero digits are significant. This has 2 significant figures. All non-zero digits are significant. When you're multiplying or dividing significant digits, the least number of significant digits is what you carry. So we have 85 kilograms, which gives me 2 significant figures, not 85.0, which would be 3 significant figures. If this thing, little g, is a negative 9.81 meters per second squared, what is g in feet per hour squared? Well, we need some equivalence statements. First of all, you need an equivalence between meters and feet. Now, you may not know this off the top of your head, but 1 foot is approximately equal to 0.3048 meters. Now, as I said, did you know that off the top of your head? Probably not. But there it is. You could have looked that up, or now I've given it to you. Now, seconds and hours. Well, if you do not know that the number of seconds in an hour, you do know that 1 minute is equal to 60 seconds, and 1 hour is equal to 60 minutes. So we could do the same idea here with equivalence. We could do 1 minute over 60 seconds times 1 hour over 60 minutes, and we would choose our arrangement so we end up with 1 hour over 3,600 seconds. When choosing them this way, the minutes will cancel. If you mixed, you'd have minutes squared per hour second or hour second per minute squared, which is going to give you a mess. Now let's do our conversion. We have a negative 9.81 meters per second squared. I'm going to multiply that by, I'll have meters in the numerator, so I need to have it in the denominator here, 3048 meters, 1 foot, times, now notice this is seconds squared. We're going to put our seconds in the numerator, 3,600 seconds, our hours in the denominator, but because it's squared here, we actually have to make sure it's squared down here. It's not simply a matter of multiplying by seconds and hours, we have seconds squared. So now we can cancel our seconds squared, we can cancel our meters, and then we simply multiply. So that gives me 1.271 times 10 to the 8th over 0.3048. Now this is feet per hour squared for our units. Now we're going to clean this up just a little bit. It gives me 4.171 feet per hour squared. We have 3 significant figures because, again, all non-zero digits. Here we have 4. Okay, because we have 0 in between non-zero and that is significant. So here I have 1, 2, 3, 4 significant figures. My process is multiplication and division, so I should only end up with 3, the least number between 3 and 4. So to proper significant figures or significant digits, I should have 4.17 feet per hour squared. Now we're going to start talking actually about some physics for a moment. We're going to predominantly work in 2 dimensions. We will sometimes get to work only in 1 dimension, and we will occasionally have to delve into 3 dimensions. We try to avoid 3 dimensions whenever possible, simply because it doesn't, in most situations, add anything at this level to the physics, but it does add to the complication. And 1 dimension, we'll do it as a segue or stepping stone to 2 dimensions. So we can think of our positions in terms of an XY coordinate, just like you graphed since you were way young. And we're going to talk about this idea of displacement, which is a final position. I use a subscript F typically for final, and an initial position of a subscript I. Sometimes you will see 2 and you will see 1 for your 2 different positions. Typically the implication here is that 2 is after 1, so this is final and this is initial. But I oftentimes like to be explicit and use an F and an I.